Now, real analysis is the branch of mathematical analysis, which is primarily concerned with the limit process and continuity of the real valued function defined on the subsets of the real line. These concepts of limit, continuity of the function and convergence of the sequence depends for the meaning on the notion of absolute value of the difference of two numbers when they are regarded as the points on the real line, which is nothing but the distance between the points. When this notion of the distance or metric for a real number is extended to a abstract sets in general, then the resulting mathematical structure are known as metric spaces. The metric space was first introduced by Fréchet, and in fact, what we want to discuss here is, we know the real line R. When we take any two arbitrary point on it, then the distance between x and y is the absolute length between x and y. That is, when we measure from x to y, either from x to y or from y to x, this absolute length we call it as the distance between the 2 point x and y. Now, this concept we wanted to extend to an arbitrary set x, because once you take the set x whose elements are certain points, how to introduce the notion of the distance between any two element of the set. Say for example, if we take a x to be a infinite sequence, set of all infinite sequence and which are bounded, then if we pick any two element x and y, both are infinite sequence. X is also x 1, x 2, x n and so on, y is also y 1, y 2, y n and so on. So, what is the how to find the distance between x and y? If I just take x minus y, then there are several points. Will it be mod x 1 minus y 1 mod x 2 y 2 etcetera, or something else. So, in what way you will introduce the notion of the distance between the points of an arbitrary set. But we should keep in mind that notion of the distance on the R satisfy those conditions must be satisfied by our newly introduced function d. Then only this d we can say it is an extension of the distance concept over a general arbitrary set. Now, let us come back to our metric space. Now, so this is the optional one, but we will discuss it here. As we have seen that in case of the real line, when we pick up the 2 point x and y, then the distance between x and y is defined as mod of x minus pi. This is the absolute distance between the 2 points on the real line, and this distance will always be greater than 0 and will be 0 if and only if the x equal to y. Then if we measure the distance either from x to y or from y to x, both will be the same. Then third is, when we take the any point z either in between x and y or maybe outside, then this will remain less than equal to x minus y plus y minus z. So, these properties are satisfied by the absolute function, or we say the distance notion function defined on the real numbers or on the real line. Then we wanted to extend it to an arbitrary set, because this is the set of real numbers. We are having this property. Now, this property we wanted to make it as an axiom for an arbitrary set, and that leads to the concept of the metric space. So, we define the metric space as a metric space x d is a pair x d consisting of a non-empty set x of elements, we call it here is point, call it points, and a notion of distance function D defined over x cross x to R which satisfies the following properties. The following properties. The first property is the distance between the 2 point PQ is greater than 0 if P is different from Q and distance between PP is 0. In fact, other way around also we can say vice versa also. So, second is distance is this, and d of PQ is the same as d of QP. Then C is d of PQ is less than equal to d of PR plus d of RQ. So, distance function is we satisfy the first is you can write the 0 property. D is a non-negative real valued function, non-negative real valued function, and this property we can also write it, that is d of PQ is 0 if and only P equal to Q. We can replace it. In fact, this is so when P and Q are identical, both are equal to 0 and vice versa. So, if these properties are satisfied, then we say this set X together with the notion of the distance forms a metric space. And one of the example is our X is R set of real line and d of x by is defined x minus y, where x and y are real. Then as we have seen earlier, satisfy all the property. Then another examples is suppose x is say R2. R2 is the 2-dimensional plane where the elements is of the form say x1, x2, y1, y2 and like this so on. So, suppose this is x element, this is another element and continue. Then d of x by, which is written as mod x minus y. I am writing just the same using the mod, but meaning of this is in 2-dimensional case it will be x1 minus y1 whole square plus x2 minus y2 whole square under root. In case of 3-dimensional, the distance between x y is defined as, we write the same way mod x minus y, but thing is the is x1 minus y1 whole square, x2 minus y2 whole square, x3 minus y3 whole square, means x1, x2, x3, y1, y2, y3. These are the coordinates belongs to R3, y, y1, y2, y3 belongs to R3, and it can be shown that these D's satisfy the condition of the metric. So, we are not going in detail, it is a part of the function analysis. So, there it will be discussed. What we are concerned is that since we have discussed it, the concept of the neighborhood, open sets, closed sets, open ball, closed ball in real line with the help of the modulus functions. So, this we wanted to extend this concept to a arbitrary metric space, arbitrary set with the notion metric space. So, let us see the few say concepts which are useful for further. So, we define let X be a metric space, let X d, I am writing X d be a metric space, okay. And then we define like this. First definition is the neighborhood. Neighborhood which we denoted by N or P, that is neighborhood of a point P with radius R. So, this we write as a neighborhood, I am writing NBD, neighborhood of a point P in a metric space, in a metric space X D, in a metric space X D is the set of all points, is the collection or is the set of all points Q belongs to X such that the distance between P and Q is strictly less than R. Then R is called the radius of this. Then R is the radius of the neighborhood. Okay. It means our neighborhood of a point in a metric space, which we denote by NRP, that is the set of those point Q belongs to X such that distance of P and Q is strictly less than R. So, this is now, for example, in case of real line, if X is R1, then this neighborhood NRP is nothing but what? Q belongs to R1 such that mod of P minus Q is less than R. That is, it is an interval. It is an interval lying between P minus R to P plus R, and Q will be the point somewhere here. So, this is the interval equivalent to the interval this interval. When X is R2, then NRP, which is Q, belongs to R2 such that mod of P minus Q, the distance, I am just writing the distance, okay, D2 is less than, this is the 2, distance 2 is less than R. That is, it is the set of all Q such that under root of this, under root of P, 2 points are there, then P1 minus Q1 whole square plus P2 minus Q2 whole square is less than R. That is where P is P1 P2, Q is Q1 Q2, both belongs to R2. So, it is a ball centered at P1 Q1 with a radius say R. So, all such point will be here. So, this is the neighborhood of this. Similarly, we can go further. Then second definition is the limit point of the set. A point P in a metric space X D is a limit point, of the set E, which is a subset of X, limit point of the set E, if every neighborhood of P, if every neighborhood of P, if every neighborhood of P contains a point Q different from P such that Q is in E, So, this is the point and limit point, means if this is a space metric space X D and here is the set E, we say this P may or may not be belongs to E, but it will be a boundary point of E if it is a limit point. Then P is called the limit point of this if every neighborhood around the point, if we draw neighborhood, means suppose in R2 we get the neighborhood in this pair and like this. So, if every neighborhood of the point P must, if includes the point Q other than P which is in E, then we say P is the limit point of the set E. Okay. Then definitions third, this is the definition about the isolated point. If P belongs to E and P is not a limit point and P is not a limit point, P is not a limit point of E, P is not a limit, then P is called an isolated point. P is called an isolated point. Isolated point. For example, suppose I consider the set E as this. Suppose I take set E as the set, or say 0 1 union set 2. Suppose I take this set 0 1 union 2 in R 2, which is subset of R 2 R, sorry, in subsets of R. So, interval this. Now, 2 here, 2 is an isolated point. Isolated point. Why? Because if we draw a neighborhood around the 2, then it does not include any point of E. So, 2 cannot be a limit point of E, but 2 is a point of E. So, it is an isolated point. And see the closed set. E is said to be closed. E is closed if every limit point of E is a point of E. Is a limit point is a limit point of E. Then E, a point P, is an interior point of E if there exists, or if there is a neighborhood, if there is a neighborhood n of P, there is a neighborhood n of P with a suitable radius such that this neighborhood is totally contained in E. So, what he says is, this is our set E. We say this point P is an interior point. If there exists a neighborhood around the point P which is totally lies inside E, then such a point P is called an interior point. Then E is said to be open. A set E in a metric space is said to be open if every point of E is an interior point of E. Interior point of E. Then this called, then G, complement. The complement of E denoted by E C is the set of all points P belongs to X. Set of all points P belongs to X such that P is not in E. H. A set E is said to be perfect in a metric space X D if E is closed, and if every point of E if every point of E is perfect, if every point of E is a limit point of E. I, a bounded set we have already discussed. So, it is a set is said to be bounded if there exists, or if there is a real number m such that and a point q belongs to X such that the distance between P and Q does not exceed by m for all p belongs to E. And lastly, we say J, a set E is dense in a metric space X D, in a metric space X D, if every point of X, is a limit point, every point of X is a limit point of E or a point of E, or a point of E, or a point of E. It means what? When we say a set, this is X, a set E, this is E, is said to be dense in this. It means every point of X, is a limit point of E or a point. So, if we take any point X, say here, suppose I take any point X here, then this point will either be a point of E, or if it is not a point of E, then it must be a limit point of E. So, limit point of means if we draw a neighborhood around the point P, there must be some point Q of E which is different from P. So, in this case the element of X and element E, they are so close to each other that you cannot separate out. As soon as you take any X and draw a neighborhood around the point X, you will always find some point of E different from this, or maybe the point itself is a point in E. So, such a case we say it is dense. For example, the set of real line, for example, our E, which is a set of rational number, and X is R, then this E is dense in R, because any real number can be approximated by means of rational number. So, if we draw any real neighborhood around the point real number, we get another real number is rational point which is different from this. So, this becomes in the last lecture we have introduced the metric space and also discussed few of the examples of a metric space. Let us take few more example which is slightly a different way. Suppose X is R cross R. This is our space X, and notion of the distance D defined on X cross X to R by D of Z1 Z2 is the length by 1 minus by 2 if x1 equal to x2, otherwise y by 1 mod by 1 plus mod by 2 plus mod x1 minus x2 if x1 is not equal to x2, where z1 is basically the point x1 by 1 belongs to x, z2 is a point x2 by 2 belonging to x. So, this is also in x, this is also in x. Now, what is this kind basically? Suppose we have the points, one point is say z1, another point is say z2. Okay. So, what we are doing is when x1 and by 1, x1 is equal to x2, the distance is by 1 minus by 2, otherwise it is this. So, if we go from here, then this is our x2, this is our x1 y1. So, x2 is different from x1. So, what we say, we take this is by 1, this is by 2. So, take the absolute distance by 1 plus this distance, this is our x1, this is our x2. So, take this distance. So, a person is coming from here, following this path, going this way and approaching z. So, this is the length between z1 and z2. We can also find the length directly. Okay. So, that will also give another metric, that is under root x 2 minus x 1 square plus y 2 minus y 1 square and square root of this. So, this is also a metric, but this is metric is known as the rival metric, because if a person wanted to cross the river, he has to first approach up to the first that river, one side of the river, then he has to cross the river and then come back to this side. Okay. So, that is called the river metric. This D, which is defined in this way, actually satisfy all the condition of the metric. The first is obviously D 1 G D Z 1 Z 2 is greater than 0, because every term is absolute, and when it is 0, and if this is 0, then what happens? Then it implies if x 1 is equal to x 2, y 1 will be y 2, if x 1 is equal to x 2. So, in that case x z 1 equal to z 2, or if this is not, if x 1 is different from x 2, then we are getting this thing. Now, sum of this is 0, sum of this is 0, it means individual term must be 0, because they are absolute term. So, y 1 is 0, y 2 is 0 and x 1 is equal to x 2. So, again this shows that z is 1 equal to z 2. Okay. So, this way d x y is greater than equal to 0 is satisfied. Second is d of z 1 z 2 is the same as d of z 2 z 1, no change, because of the modular sign there will not be change in the value. And third is d of z 1 z 3, where z 3 is a point x 3 by 3. So, z 3 is another point, say x 3 by 3, here we can say z 3 another point x 3 by 3. Okay. So, if we find the z 1 z 1 z 2 and then z 2 z 3, we see z 1 z 2 is this distance, while z 1 z 3 will be this distance, this, and then z 3 z 3 again this and this. So, it will be less than or equal to this. Therefore, triangular inequality is also satisfied. So, this forms a distance on x cross a metric on this x. Another example of this metric on the R, we can also introduce the metric d of z 1 z 2 as mod x 1 minus x 2 plus mod y 1 minus y 2. Say z is x 1 y 1, z is x 2 y 2, take this distance. So, mod of this plus mod of this, okay, mod of entire thing z y 1 minus y 2. Now, this also forms a metric and we see all the conditions are satisfied. Therefore, this will be metric. Okay. Now, this shows that over a set X one can introduce in more than one base the metric for it.